So this is the first section of Chapter 7, and we're going to talk about how to calculate the volume when we take a function and revolve it around one of the axes, the x or the y-axis. So again, we're talking about an integral process that's going to explain a physical quantity, and that physical quantity is volume. And so in the picture here, we have the Limerick generating station in Pennsylvania. And so for this one, we're talking about a exhaust stack here that has a contour that resembles a parabola. And they call it natural draft hyperbolic cooling tower. So it's a hyperbolic shape. Natural draft just means that the hot vapors raise up and out of the top of the stack. So it's 507 feet tall. So the question is, eventually that we'll answer, is what's the volume of the water vapor that's coming out of the stack. So these are not in your notes. We're just going to kind of talk about some basic, just kind of give you a mental picture of what happens when we rotate a function about an axis. So we're going to rotate the line g of x equals 3. So it's a horizontal line at 3. And we're going to rotate this about the x-axis, so an axis that's parallel to it. We'll rotate this function from 0 to 4. So we have a domain here, a starting and a stopping point, so to speak. And so we're going to rotate that about the x-axis here. So I have a video of doing that. So I'm going to change the function here. And that's going to be 3 for g of x equals 3. And we're going to eventually see that function come across here. And then I'm going to change my limits here from 0 to 4. So it's going to eventually get that function to go from 0 to 4. And then we're going to go ahead and rotate that. We're going to spin it about this axis here. So we do that by sliding the slider here. So we can kind of see that function in 2 dimensions, like we would graph it on a piece of paper. And then with GeoGebra here, we're allowed to get that 3D model for you to get that picture of what it would be like in 3 dimensions. So we're going to slide the rotation slider. And as we do that, you'll see this volume generated. And as we rotate it all the way around, you can see that we get that cylindrical shape. And this dark disc in the center is what we call a representative disc. And we'll talk a little more about that when we get into the calculus involved. So then we have that 3-dimensional shape when we rotate the horizontal line about the x-axis. And so we're going to then talk about that solid revolution and how we can calculate the volume of this. So you're going to notice here that this is a geometric shape. It's a cylinder, and so we really don't need the calculus to calculate the volume of this. We can use some geometry formulas to calculate the volume of this. But we're going to start out with this shape and figure out what we could do from a calculus standpoint to get the volume here. So if you notice, if we slice this cylinder, we would create this flat disc surface. So if we would take a slice out of this, kind of like you're slicing a slice of cheese or something, and we would get this skinny flat disc. And if we notice, if we started stacking a disc of this size at x equals 0, that we could stack those discs of identical size all the way out to x equals 4. So if we do that, then we can accumulate those discs that are all the same size. And if we go from 0 to 4, then we have enough discs to accumulate the entire shape, or to make the entire shape. So if we take a look at just this single disc here and talk about its volume, then here's that single disk. Then the volume of that single disk, if you remember back to geometry, is going to be the area of the base times its thickness. And so this thickness is so skinny you can almost barely see it. You can see it better in this picture. So if we talk about calculating that volume, then we need that radius of that disk, and we need the thickness of that disk, and we're going to call that thickness dx, since that thickness lies along the x-axis. So then that volume becomes pi times radius squared times the height or the thickness of that disk, and that's where our dx is going to come in. And so if we talk about the radius then from a calculus standpoint or an algebraic standpoint, you could even call it, that radius really is the function itself. So the volume of this disk then is really pi times g of x squared, right, pi r squared, times the thickness of that disk, which is dx. So if that represents one disk, then what we can do is we can stack them up from 0 to 4. And then we have that accumulated volume, so to speak, of the cylinder that we see. So we can extend that then to any function that we decide to graph. And if we rotate it about the x-axis, then we end up with that dx problem. So here's our pi times our radius squared times dx. So that radius is going to be, in this case, the function if we're rotating it about the x-axis. And then if we rotate something about the y-axis, then we're going to be stacking those disks vertically. And in order to do that, then the radius is going to be measured off the vertical axis. So the radius is going to be a horizontal distance, or a distance, and so we would have to rewrite the function so that we get it in terms of y. And so that cylinder ends up being then pi times the function in terms of y squared times dy. So so there are the two methods by which we'll be calculating the volume of a solid. And so let's take a look at this function. And if we notice that function is linear, so it has an intercept of 2 and a slope of -0.5, so down 1 over 2, down 1 over 2. And we're going to rotate this about the x-axis, so we're going to spin it about this axis here. And so when we do that, back in the video of GeoGebra here, so I'm going to put in 2 minus 1/2 x. And I didn't mention any bounds, but if we take a look at that shape starts at y equals 0. That's its base. Or excuse me, x equals 0, and it goes to 4. So we're going to stick with the same limits we had in the previous one. And then we're going to spin that about the x-axis. So as the video is playing here, I'm just going to draw your attention to this line here between 2 and 3. As we rotate, that's my representative rectangle. It's just really skinny. And I'm going to rotate that around the x-axis to create that disk. And so that whole line is going to follow with me and create then that three-dimensional shape. And as you can start to see, as we spin that line, that three-dimensional shape is a cone. And again, you know, if it's geometric, we can use geometry. There's nothing wrong with doing that, even on a calculus exam. But we're going to look at that cone and find the volume of that cone. But now you might notice that that representative disk, that black disk right here between 2 and 3, it's going to have a different size to it. It's always going to be a disk, but it's going to have a different size to it, depending upon where we locate it. So that disk, if we locate it at the bottom here, that disk is going to have a radius of 2. And if we locate it right at the tip, it's going to have a radius of 0. So this is where the calculus becomes a little more necessary, since the disk is changing size. Although I would argue that we could use geometry here too, since we have a linear function. So it's going to create a flat curved surface. So if we look at this volume, Then looking at the axis of revolution, we know that we're going to come, this is the x-axis here, we're going to come out of the screen, so to speak, and spin it out towards you, and then we're going to come back into the screen and spin into the screen, or maybe behind the screen, like you saw in the animation. So here's that representative rectangle. That's what creates our disk when we spin it. That was that black, thin rectangle in the video. And so we see that if this is the axis of rotation and the top of the disk ends up here on the function, that this ends up being the radius of the disk. And so that's going to factor into our volume expression. So that radius, since it goes from 0 to f of x, that radius is just f of x, or just the value of the function itself. So as we then set up for the volume here, we know that the thickness of the rectangle is always our differential dx. Our radius is going to be our function. And if we notice that when we're just kind of noticing some patterns, we notice that this representative rectangle is perpendicular to the axis of rotation. Remember the perpendicular sign from geometry? So we're kind of acknowledging that we're always drawing the rectangle perpendicular to the axis of rotation for this method. And then that's how we can get that disk when we spin that rectangle perpendicularly around that axis. So here's our representative disk. It's got a radius, and that radius goes up to the function 2 minus half x, and it's got a thickness of dx. And so we notice a couple things about this representative rectangle. First of all, it's really not flat on top, right? It's really more trapezoidal, but that's okay because that is all factored into the integration. So as we set up the volume then of the disk expression, we get pi r squared times the thickness. And so we know that our radius is our function, so it's 2 minus half x squared. So we have a little foiling to do here, and we know the thickness is dx. So we're going to go ahead then and set up the integration for that. So this is our disk. We're going to stack those disks from here to here, which means from 0 to 4. And then we're going to go ahead and stick our disk expression right in here, pi times 2 minus half x quantity squared dx. And then we're going to have to FOIL. So the first thing I do is pull out the pi. It's just a constant. I'll put that out front. And we're going to go from 0 to 4, and we're going to FOIL this. So we have 2 minus half x times the quantity 2 minus half x. So we've got 2 times 2, which is 4. And then we've got 2 times a half, which is 1, actually negative a half. So 2 times negative a half is negative 1, and then double that, we get negative 2x. And then we have to square this, which is positive 1/4 x squared. So that's the binomial foiled out, and then now we can go ahead and integrate that. And so integrating 4, we get 4x. Integrating minus 2x, we get really minus 2x squared over 2. I just am starting to simplify this as we get better with our integration. And then integrating this, we get 1/4 times x cubed over 3. So when we simplify that, we get this. And then we can go ahead and stick 4 and 0 in and evaluate this volume. So when we stick 4 in, we get 16 minus 16, that's interesting, times 64 over 12. And then when we put in 0, we get zeros in all these. So we must have 64/12 pi. That can be reduced, but it's really not necessary to reduce it. We just leave it as 64 over 12. So let's talk about using geometry here, because we could. And there's nothing wrong with using geometry. In fact, if you get this question on an AP test, which is entirely possible, especially for a multiple choice question, because it's as you practice this will become a really quick question. If you get anything geometric, please use geometry if you prefer over calculus. That's totally legal on any part of the AP test. So let's talk about the geometry in this situation. So when we look at this and spin it, there we go, we can see then that it is a cone with a base here as we kind of see it in geometry with a radius, and that radius of the base we'll talk about in just a few seconds, but probably easier to count the boxes here. And then that height of that cone. So we're talking about then the volume of a cone is 1/3 pi r squared h. And we have a radius of 2, 1, 2. And we have a height of 4, 1, 2, 3, 4. And so when we plug those numbers into here, we get 1/3 pi times 2 squared times 4. And so we have a volume of 16/3 pi. So if you remember the answer from the previous page, which was 64/12. So 64/12, factor out of 4 ends up to be 16/3. So we just kind of verified that answer using geometry. Now let's talk about what happens when we revolve about a y-axis. So in kind of a similar sort of scenario that we had with areas back in the previous section where we had dy and dx problems, we have that same situation with volumes. We have dy's and dx problems. So this is a dy problem. So we're talking about taking x squared. So here's x squared, it's a parabola, but we're only going to go from 0 to 2 on the x-axis. And we're going to spin this around the y-axis. And so again, draw your attention here between 2 and 3. This is going to be our disk as we rotate that function. So, and I might point out over here with this GeoGebra file, I show you the setup and I show you the answer just to help you gain proficiency. But this is definitely a question. All these questions are definitely ones you should be able to navigate without a calculator, but these are just here as a support structure for you. So we're going to go ahead then and use our rotational slider here to rotate that about the y-axis. And as you can see, these disks are now vertical along the y-axis, so they're dy disks. And those dy disks are going to be stacked from bottom to top, which is going to change our limits of integration. We're going to have to look along the y-axis for those limits now. So there's that disk, and if you might notice that that's a very similar shape to some of the foam pieces that are at the front of the room. It's a common shape that students make as part of their final project when they decide which solid to create. And so we get this kind of cone-shaped sort of thing. Kind of like a nose cone or something like that, a gumdrop, so to speak. So if we then talk about the calculus involved here, here's that original picture of the function graphed in the xy plane. And so as we rotate about the y-axis, you can picture this coming out towards you and then going back onto the screen, and then picture going maybe into the screen, back around to the beginning. So there's that representative rectangle that creates the disk. And we're going to stack those disks from something really tiny, in fact it's a disk of 0 radius, all the way up here to a disk of a radius of 2. So when we stack these things, we're going to have to stack them vertically from 0 to 4. So that radius then is just the x coordinate. And so what we have to do, I mean, it's measured horizontally from x equals 0 out here to some x value, if we were looking at this specific location. So that x value we can find by taking this function and getting it into x equals form. In other words, solving it for x. Or we could also call that writing it as a function of y. So all of those things all of those phrases I just kind of threw out there mean the same thing. Okay, x equals a function of y. All of those two phrases just mean solve this so that we get it in x equals form. And so we notice also that the thickness of this disk is a dy. So we know this is a dy problem. So we know then we have to call this y and get that then expression in terms of y. And then I threw up our geometric perpendicular symbol again because we're acknowledging that this axis of rotation is perpendicular to this rectangle. That's how that disk is generated, by spinning that rectangle around an axis that's perpendicular to it. So there's that final solid with our flat disk here. So we can see that radius of that disk comes out horizontally, a distance of x, distance of the x coordinate. And so we're going to go ahead and get that x equals expression. So the first thing we're going to do is call f of x y. We're going to get rid of that function notation, and then we're going to solve this. So we're going to square root both sides, and we have x equals the square root of y. So now we can go ahead and set up then that, that's our radius. We can go ahead and set up our volume. So, so looking at this, then we know that we're going to stack these from 0 to 4. And it's going to be pi times that function, that g of y, so to speak, that function in terms of y squared. So if we look at here, that radius is the square root of y. So it's the expression then is from 0 to 4 pi times the square root of y squared dy. And if we simplify this, we can see then we've got something that's pretty quick to integrate here. So I pulled the pi out front, factored that out, that constant out, and then I have to integrate y, which is not too bad. That makes me happy. It's pretty quick integration. So I integrate y and get y squared over 2, and then I can plug in my 4 and plug in my 0. And so when I plug in 4, I get 16. 16 divided by 2 is 8. 0, this makes this 0, so I get 8. This whole thing in the brackets is 8. 8 pi units cubed, because we're talking about volume. So 8 pi is somewhere in the neighborhood of 25, if you wanted to approximate it. But certainly 8 pi is an exact answer. Especially in a multiple choice, we would be looking for that in our answer selections because they would leave it in terms of pi. So back to our cooling tower on our nuclear plant. If we model this with an equation, that equation looks like, if the top of the tank is 500 feet, that equation that we're talking vertically, so we're going to have a dy disk here. And so getting that function in terms of y, right, getting that x equals expression, the function of the water tower is basically that expression. And as we then use this as our radius that creates our disk, then we're integrating from 0 to 500 pi times this squared. So we're going to set that up then, 0 to 500 pi times that expression squared. And we're not going to FOIL that out. This is definitely an opportunity to practice your FN int. So if you go ahead and FN int this, we're looking at something that is about 24 million cubic feet of water vapor that can be held into this cooling tower. So at this point, you should be able to go ahead and start the day 1 homework for creating volumes using the disk method. The proficiency quiz, you might want to wait till day 3. We've got a couple other things to discuss. GeoGebra has an app for the iPad. And so if you want to use the modeling files that I've been using in class and in this video, go ahead and put the app on your iPad. And then in the Unit 7 Google Drive folder, there is a GeoGebra file folder. And you'll find that disk method file in there. And you can start putting in the functions that you're seeing on your homework and modeling those to get a good representation of what's going on there.